Hello everybody and welcome to this computer architecture lectures. Today we're going to talk about number conversions. Remember, in the first lecture we found that the computer doesn't work with numbers, but it actually has voltage levels or current levels or maybe charges or resistance states. It doesn't have numbers, but we found out that actually we can map the physical world onto the mathematics world, and we can imagine there to be Boolean logic levels, for instance, at the entrances of logic gates. Or we can have binary logic levels, ones and zeros, if we want. Or actually when we combine various entrances or bits, then we can actually have binary values. Or we can have decimal values and hexadecimal values. So now it is time to talk about the base systems, the number systems. And we did this in the last lecture. And then we said that actually we make the convention, a simple convention, that we write any number as something like A, B, C, D, E for 5 digits, and the base in which we always have to specify the base in which it is written. So I gave you the example last lecture, 1, 2, 3, 4, 5, base 6. It means that the last digit on the right is multiplied by 1, the one before that is multiplied by the base, before that is multiplied by the base squared, then by base cubed, and so on. So having said this, actually conversions, when we just listen to what this means, then the conversions are actually quite simple. That is to say, the idea is simple. Doing the things may still be a little bit complicated. But let's take here a look at a lengthy example. Imagine we have the number 234, not 234, but 234 in base 5 system. This means that the digit 4 is multiplied by 1, the digit 3 is multiplied by 5, and the digit 2 is multiplied by 5 squared. Or let's do it converting to base 10. So what do we have to do? Any conversion from any base to any other base, what we have to do, we have to express all elements in the destination system. So in this case, we want to convert to base 10. It means we have to multiply 2 by 5 squared, plus 3 times 5 plus 4 times 1. And that, fortunately, is very easy, and we're already used to this because we're used to doing calculations in base 10. That's very easy because we know from the table that 2 times 5 squared is 2 times 25, and that's 50. Plus 3 times 5, that's 15, plus 4 times 1 makes a total of 69. So conversion from base 5 to base 10 is actually quite simple. Now converting from base 5 to base 2, I have also given an example here. We are not so good at multiplying this, but computers are very good at this. Actually, much better than we are. So what we have to do, 2, 3, 4, we have to express all elements in the destination system, and that is binary. So 2 is actually 0, 1, 0 in binary, as you hopefully by now already know. 5 squared, that would be, this one is multiplied by 5 squared. I could show you here the calculation, but this one you will just have to believe me. You can also do it, just stop the video and do the calculations yourself to see if you can do this to calculate 5 times 5. Multiplying in binary or in any system is shift-add operations. So I will do actually an example of this one. But first I will tell you that 010 times 11001 is simply multiplying by the base, is simply adding a 0 at the end. So this value is written here, is 110010. This calculation I will show you a little bit in more detail, because 011 times 101, that is 3 that we got here, times the base, that is 5. So what would that be? 011 times 101, well, that is 1 times 101 that I have here, plus 10 times 0 times 101, and that is a left shift of 1 of this of this number, and that is 1, 0, 1, 0. Adding them together would be 1, 1, 1, 1. So 3 times 5 is actually 3 times 5 is 0, 1, 1 times 1, 0, 1, and that is 1, 1, 1, 1. So we add that to our sum. And the last one is quite simple. 4 times 1, 4 times 1, that is simple. 4 in binary is 100 times 1, so that is just 100. So now we can add this all together. This comes from 2 times the base squared. This comes from 3 times the base, and this comes from 4 times 1. Adding them all together, we get this. 0 plus 1 plus 0 gives 1. 1 plus 1 plus 0 gives 0 plus a carry. The calculations are actually very similar to decimal calculations. So we get a carry. Carry plus 0 plus 1 plus 1 is 1 plus a carry. Carry plus 0 plus 1 is 0 plus a carry. Carry plus 1 is 0 plus a carry. Carry plus 1 is 0 plus a carry. Carry plus nothing is just 1. So now we have in binary the number 234 in base 5 is equal to 69 in base 10 is equal to 1000101 in base 2. To see if our calculations are correct, let's do the calculation now, conversion back to base 10. So 1, this is times multiplied by 1, this is multiplied by the base 2 squared, which is 4, and this one is multiplied by the base to the 6th power, which is 64. So 64 plus 4 plus 1, indeed, that is 69. Now let's go back converting to base 5. Base 5, this is a little bit more complicated, but remain calm and you will see it. How much is 6 in base 5? 6 is 1 times the base. 5 plus 1 is 6. So 6 is 1, 1. And that one we had to multiply actually by the base in which it was expressed, which is 10. Well, 10 in base 5 is 2 times 5 plus 0. So that is 20. So 6, this 6 is actually 1, 1 times 20 in base 5. 9, which has to be multiplied by 1. 9 actually is 1 times 5 plus 4. So that is 1, 4. 1, 4 times 1. Then we can do the calculation. 1, 1 times 20 is 220. 1, 4 times 1, that's easy, that's 1, 4. And we can add them together and we get 234 in base 5. Or I should say, I should not make the mistake, 234 in base 5. So everything seems to be adding up well. From base 5 to base 10, from base 5 to base 2, from base 2 to base 10, and from base 10 to base 5. The thing you have to remember is express all elements that you see in the destination system and everything will work out fine. Now, having said that, this is not how many people actually are doing the calculations. And that is because most calculations are done decimal to binary. Actually, humans are decimal, computers are binary, so what we're doing all day is decimal to binary and binary to decimal. Binary to decimal I've shown already on the previous slide, but decimal to binary is a little bit special, often used, and there's another technique to use, which is just successive divisions by the base, in this case base 2. So we, for instance, if we have 234 base 10, so now it is 234, what do? We do successive divisions. 234 divided by 2 is 117, and we don't have any remainder. Then we divide by 2, we have 58, and we have a remainder of 1. Forget the remainder, continue with the 58, divide by 2, you get 29 and no remainder. Then divide by 2, you get 14 and a remainder of 1. Forget the 1, continue with the 14, divide by 2, you get 7 and no remainder. Divide by 2, you get 3 and a remainder of 1. Continue with only the 3, divide by 2, you get 1 and a remainder of 1. Forget the remainder, divide by 2, you get 0 and a remainder of 1. And because we have 0, we have finished, and we can now read the binary number from bottom to top, which is 111001. To calculate if it's correct, let's convert back from binary to decimal, which is multiplying the last digit by 1, adding and multiplying the last digit by 2, plus the digit by 4, 8, 16, 32, 64 and 128. So it is 128 plus 64 plus 32, not plus 16 but plus 8, not plus 4 but plus 2, not plus 1. So that is, if you do the calculation, stop the video anytime you want and you will see that this is 234 in base 10. Now, the conversion from any number system to any other number system, this should not cause any panic. Remain calm and do your conversions.